All right, let's keep on with some more ways in order to integrate. So what if I'm given this? The integral of cosine x plus sine cubed x all over secant x dx. Now remember, in that first example, I said your best case, or not the first example, the second one, your best case scenario is when you have a monomial in the denominator. You use that and you split it up, right? You split that up in there. So what I actually have, let me go back to blue. I actually have cosine of x over secant x plus sine cubed x over secant x. Right? Okay. Now, do your thing. If I'm looking at secant, we know is a reciprocal identity of cosine, so if I move that up, I actually have cosine squared of x plus sine cubed x cosine x dx. Now, here's a new, well, not a new identity. It's still an identity you learned in trig, but it's one we haven't used before. So we're going to be using another identity. In this one, we're going to use quite a bit. Remember, I'm going to say, if I have cosine squared of x, that's the same thing as 1/2 1 plus cosine 2x. It's the double angle identity. Sometimes I call it power reducing because I start with something that's squared and I break it down to just a double angle. All right. Sine is the same way, except it's a minus. Still cosine, but then it's that minus. All right. Okay. So for this one, typically I don't split up integrals, but the option is available to split up integrals when you need to. And in my situation right here, I need to, because I'm going to solve this one differently than I'm going to solve this one. So let's do it right now. I'm going to split this up to be cosine squared x dx plus the integral of sine cubed x cosine x dx. I'm going to start here with integral 1. And I'm going to call this integral 2. So because I'm going to solve them differently. All right, so I'm going to scoot this up. Integral 1, I'm going to use my power reducing identity. So 1/2, it's just a coefficient, so I throw that out front. 1 plus the cosine of 2x dx. Now that you can straight up integrate. So I've got 1/2, and here I've got x plus, and now remember, with this 2 inside, I'm going to put the 1/2 in front here because it's just that numeric, so it's that reverse chain with that numeric that's in there. The antiderivative of cosine is sine, keeping those guts, plus c. All right, you can distribute that, pardon me, you can distribute that 1/2 if you want. And then there's integral 1. Let's take a look here at integral 2. So for integral 2, we're going to use a u sub. All right, so u is going to be sine x, and du is the cosine x dx right there. There's my du. So I actually end up with u cubed du. Do you see that? And a lot of the stuff coming out of 8.1, you're going to see again in subsequent sections in Chapter 8. We're going to do a lot with trig integrals. We have a whole section on it. So we'll dive into this part a little bit more with trig integrals, but right now you can see, all right, what is my u sub here? What is something? My u always is the crazy thing, and this one has the exponent on it. That makes it the crazy thing. So that's my u, and my du subs right out. Okay, so now when I antiderivative this, I've got 1/4 u to the 4th plus c, and sub that back in. So integral 2 is 1/4 sine to the 4th x plus c. And then I put them all back together. 1/2 x plus 1/4 sine 2x plus 1/4 sine to the 4th x plus c. And I am 100% on board with you leaving that in that way. You don't have to factor out the fractions. You don't have to do any of that. You can just leave it just like that. All right. So if you need to split up your integrals, you can. You don't always need to do that. The defining characteristic of this one is the fact that you have a monomial in the denominator. So you can split up those fractions. I'm going to do one more example like this without trig, just with, so here is, let's call this example 4 again, is what we'll call it, right? So it's that monomial in the denominator split up situation. X cubed plus the square root of x all over x to the 3/2 dx. The two we've done so far has had trig as a monomial. It doesn't have to be trig. Doesn't have to be trig. You could have a single term down here. Let me make this red. A single term down here, that's a polynomial that you can split up also. Then you just divide. If I have like bases, you subtract the exponents. What is 3 minus 3/2? Yes, 3/2. All right, 3 minus 1/2 is 3/2. Here, let me, wait. I'm going to put this extra step in here because I really want to make sure you see this. X cubed divided by x to the 3/2 plus, and I'll change this as x to the 1/2 over x to the 3/2 dx. Do you see that now? Okay. That's what we're really doing. So now I have x to the 3/2, and then this one, 1/2 minus that x to the 3/2, that's going to leave me with 1 over x dx. I almost put plus c. That'd have been bad. We're not there yet. We're still in our differential phase. Tell me, why would I leave this in terms of a 1 over x instead of x to the -1? Right? This is not a power rule. 1 over x is natural log. Look for those patterns. This is the power rule. This is natural log. If there's just an x by itself, that's natural log. So I'm going to add 1 to that. Plus 2 over 2, right? That's going to give me x to the 5/2, bringing that 2/5 in front. That's just Calc 1 stuff. Plus the natural log of x. And that's our final answer. I just wanted to do one like this because I want you to see you don't always just have to have trig as the monomial in the denominator, right? If you have that monomial, you split it up so you can just algebra that down into something you can actually integrate. Okay.